Well, I think what I'm going to start with today is in your notebooks, the handouts, SB page 151 has some really good problems. And I like to bring these up because if you go to, actually even in our own textbook, okay, these kinds of problems, they tell you to solve these by taking the log of both sides, okay? But there's a much easier way to do these, all right? If you notice, if you notice two numbers that have a base that can be expressed in the same base, like 4 and 8 are both base 2 numbers. It's going to be far easier to solve it that way than taking the log of both sides. So I'll only take the log of both sides, which we're going to get. We're going to tackle one of the ones that you have to do it if you can't express the two numbers in the same base. But notice how much easier it is. I've already introduced you to this technique, so it shouldn't be brand new. Let's take a look at problem number 1 here, right? 4 to the 3x plus 5 is equal to 8 to the 4x minus 3. And you know, if I take logs, then I've got, what I'll have is, so this is what they tell you to do. Take the log of both sides. Let me think about this for a minute here. The log of 4, 3x plus 5 is going to equal the log of 8, 4x minus 3. And then you bring this over, and then you turn these into logs, and it's like, it goes all the way down the page. And to me, it's just a ridiculous way to do it. If you notice that you've got 2 base 2 numbers, right? So don't make things more complicated. And I do not know why, but every book I have seen does not teach you to do this. I don't know why. Maybe they just feel like, oh, well, maybe you would notice that and do it on your own, right? Okay, but notice this is going to be far easier because now what am I solving? I'm just solving this is equal to this. I have two really simple linear. I can just, the bases go away, right? Okay, eventually I'll get there if I take logs, but so I end up with 6x plus 10 is equal to 12x minus 9. Subtract my 6x from both sides. Add my 9 to both sides. I get 6x is 19. X is equal to 19/6, which wouldn't have been at all intuitive looking at these numbers, but if I plug that number into these, right, I will find that this is equal to this. And again, on a test, the Chapter 4 test is, I believe, the shortest test of the year. It's like 3 pages long. It is the shortest test. You got plenty of time. It takes about an hour. So you got plenty of time to plug things back in and make sure they're equal to each other. It's like almost no excuse for getting them wrong, right? Okay? Okay, so now if you look at number 2 on the page, so what's interesting, we're gonna be morphing into 4.5 here very shortly. It's solving equations. But to me, if I take something like this and put it in log form, that's already gonna solve the equation. I know I need to do that because the variable is in the exponent, and the only way to solve that is to get it out, right? And that's to unbundle it with a log. So for this one, how would I express this how would I use the log? And again, I'm not going to take the log of both sides. That's another thing. I have people take the log of this is equal to the log of that, but shoot, I mean, I already know how to express this in logarithmic form, and that'll give me the equation. Does that make sense? Mm-hmm. Okay, so if I have e to the 8 minus 3x is equal to 268, well, if I'm going to take the log of base e, it's going to be the natural log, right? I could just put the e down there if I want to. E to the exponents over here, right? 8 minus 3x is equal to 268. And just think, e to this is equal to that. I've just re-expressed it rather than have logs on both sides. Okay? Got it?
Yeah.
So you'll never see me take the log of both sides. I mean, notice what happens if I did do that. If I said, hey, the natural log of this is equal to the natural log of this, well, e to the e means that goes away, then I get that, that's over there, this is over here. I mean, it does work, but I find it has served me better to take something that's in exponential form, simple exponential form, and just put it in simple logarithmic form, okay? And then from here, this is a number, right? Okay?
Mhm.
So if you notice, to solve this, natural log of 268 minus 8 is going to equal negative 3x, right? And then divide by negative 3, and that's what x equals, this. And you can plug this into your calculator and get an answer, which would be, why don't you do that, just to make sure you could do that correctly. That's the other thing, is it's such a shame when people miss questions due to calculator errors. X should be about
Negative 86.6.
Nope, it's not going to be correct. So see what you did, find out what you did wrong.
Oh, the natural.
Parentheses, or did you use
it
log instead of
11?
natural log? There
I
you go.
forgot to plug
Is
in the natural
11
log.
point?
Nope,
Okay. Is it 8.25?
yep,
So
that's what, it should be
Yeah.
about 8.03, right?
Mhm.
That's what I have on my key anyway. Am I wrong?
okay.
Let me do it.
We'll do it.
Okay,
Yeah,
so
negative one.
did you get the same answer?
Mhm.
Okay, so I'm going to do natural log of 268, okay?
Oh, yeah.
Notice you have, if you're going to keep going, close the parenthesis, right? Minus 8, is that right?
Yes.
And I would hit enter, and then I would divide by negative 3. Yes. Are you raising your hand, Onyx? And there you go.
Yeah, I got I got closer to 8.25. I got 8.25.
So I'm going to share my screen. You're going to see my calculator strokes. And that's what you should get. Okay? Natural log of 268 minus 8, I get that. If I divide that by negative 3, I get 0.0803. Like I said, you get this far if you can't get an this is in all of your science classes, instead of when you're using logs, you're going to need a number, right? So make sure you can get the number out of that. Can you figure out where you went wrong on that, Onyx?
It's weird though. I did it all in one step.
Okay, watch what happens. Watch what happens if you do that. It's a PEMDAS thing. What if I do that and then do divided by negative 3? That's wrong. Because what I'm doing, it's doing PEMDAS. So what that is saying, take the natural log of 268, then subtract 8 divided by negative 3.
Oh.
It's only dividing the 8 by the negative 3, not the whole thing. So that's why I tend to do these in 2 steps, unless you'd have to put parentheses around this whole expression, which is kind of a pain. So I'll just tend to do that, enter, then divide by negative 3. Okay?
I gotcha.
Yep. And then how would I know if it was correct? Well, I could plug it back in, right? If I say, hey, second function, there's my e. Well, I should have done the other one, because I'm going to raise it, right? So, e to the, I'm seeing these, okay, 8 minus 3 times, and then I'm going to grab that number up there, right there, and there's my 268, okay? So if you plug your answer back in, you should be able to get the original expression, right? Okay? And that's why I actually recommend doing calculator practice, because it's really easy to make mistakes on the calculator, right? Okay? Anybody have any questions on that? That's a really good one. Okay, let's go to number 3. Same thing, right?
Yes.
It's a simple logarithmic expression. I mean simple in that I only have an exponential on one side of the equal. Where they get complicated is when I have an exponential on this side, an exponential on this side, and I can't express them. That's the only option I have, is to take logs on both sides, okay? We'll get there in a minute. Let's do 5, everybody's gonna be so excited for those. You have no idea how much fun those are. There we go. This is just like the other one we just did, right? Okay, so this one, because it's a base 5, I mean, I don't know, maybe I could do, hey, the log of that is equal to the log of that, and then you just simply put that in front, right? So this, I'm gonna do this the log way. But I think it's easier just to do it. I'm just gonna show you it does work. The log of 761, right? Divide both sides by the log of 5, right?
Yes.
There we go. Wait a minute, I don't wanna do that yet. Good grief. By, wow, I almost messed that up. This is why I don't do this. It's plus. So I'm going to subtract 7 times minus 7 times the log of, again, there's a reason I don't do it this way. Minus 7 times log 5, right? All of that, this gets rid of this, and then I have to divide a whole thing by 6 here, right? All that to get x all by itself. So yeah, this is, I'm juggling 2 logs here. And I'll get to the right answer. And like I said, every YouTube video I've ever seen and every book example I've seen tells you to do that. But let's go back to the original. Do you see why I would prefer to say, hey, the log of base 5, here's my answer, 761 is equal to this. It's just simpler, right? Only 1 log to juggle, much less likely to make a mistake. So then I'm going to subtract 7 from both sides, right? 761 here, give myself a little room. Minus 7 gets rid of that. Divide that by 6. And again, let's see if you guys can come up with an answer for this one. A little more calculator practice. This one here, I might do this as my change of base first. I'll practice the calculator entries. I'm gonna do this in little steps, okay? Clear. Okay. So I think the first thing I'm gonna do is I'm gonna take the log of 5, is that it? The log of 5 divided by the log of, what is it, 761?
Yes.
Okay. And so that is this part here. I've just done that enter, okay? Then I'm gonna subtract 7. I'm just gonna do it the way I should do it if I was doing PEMDAS, right? Then I'm gonna subtract 7, and then I'm gonna take that answer and I'm gonna divide by 6. And I get about negative 1.126, right?
Yes. So I have a question.
Sure.
Because didn't you say?
Oh, I did it backwards.
Yeah. And
Sorry about that, guys. Thank you. 1161. Log of 761 divided by log of 5. I'm looking behind me and I reversed it. Okay, there we go. Then I subtract 7. I would have caught it because I was going to plug it in, but it wouldn't work. And then I'm going to divide by 6. And now I'm going to get negative 0.4796. Negative 0.4796. Stop when I get to the 1s, right? Plug that back in. So now I'm going to do 5 raised to the 6 times that number, right? Plus 7. And I get 761. Now I know it's right. I didn't have that on my key, so write that in there. About negative, what do we say, negative 0.4796. Okay. good practice. What about problem 4? Exponentials on both sides, right? What do I have to do? What should I try to do first?
Same base?
See if I can express them in the same base. Can I do that?
Yes.
1 over 27 and 9 are both base 3 numbers, right? So my 9 to the 2x, is that a minus or that's a plus? Wow. My copy is, for some reason, didn't print quite right. Raised to the 3x plus 1. Okay, express this as 3 squared times that 2x plus 3. And this becomes 1 over 3 cubed, which would be 3 to the negative 3, right? So we reviewed all those properties earlier. And now I've got this equal to that. Okay? Add 9, subtract 6. Give it a nice rational number there. The only thing at this point calculator-wise would be if I was doing a quiz or a test, I would take this and I would plug it into each expression to make sure that they do in fact equal each other, right? Everybody hanging in there? Okay. These are they're a little bit more involved, but we're still not like in the crazy hard. Yeah, right? What type do we have for problem 5? It's just I would call this a simple exponential, right?
Yes.
Because I have a base, an answer, and an exponent. Easy enough. Just simply express this as a log. Right? Log 380. If that was 81, I wouldn't bother to do this,
No.
right? I would have 4 is equal to that, right? But it's 87, not so convenient. Plus 5 is equal to 2x, which means I divide by 2, I get x. A couple steps in my head. Right? So add 5,
Yep.
then divide by 2.
Okay.
If you make mistakes on that, or if it's a quiz or a test, you might write out a little bit more than that. But that is a number. I'll do one more on the calculator just for the fun of it. I do have an answer on this one for my key, so I'm going to make sure I do this right. The log of 87 divided by the log of 83, right? That's my change of base. The log of 3, is that what it is?
Yes.
Keep looking behind me, and so I'm going to show this over so you can see it, right? So we're going to do that's this part. Then I'm going to add 5 to that.
Yes.
This way I just don't have to worry about parentheses, and then I'm going to divide the whole thing by 2. And I get about, what do you get?
4.53.
2.5, if you want to keep going out, however far you want to go out, right?
Yes.
And then you just plug it back in to check it. I did check it, okay? All right. I'm going to do number 6. What type is this one, Michael?
Natural log.
It's going to be a natural log, yes. Do I have to, what's my first step on this one?
Would be to divide by 4.
Yeah, you want, before you take a log, you need to isolate the function, right? This is a function, so first I'm going to divide by 4. Does everybody see that? To get that. Now I can re-express it, okay? So now I get a natural log, right, of 195 over 4 is equal to 3x minus 5. In my calculator, it might be easier to say 195 times 0.25, then I don't have to worry about divisioning, right? Then I'm gonna just say, actually, I'm gonna do it that way in my calculator, right? Plus 5, adding 5 to both sides, divide by 3 is gonna equal to x. Enter those two simple solving equation steps. And one last time. Just practice a quick plug-in, see what you get. That's what you should get.
Yep, 2.962.
Everybody good now? Hanging in there. Hannah, how's this going for you?
I'm processing.
You're practicing. That's what you're supposed to be doing. Good. These are really good practice problems. So, right? Okay. Are you having problems getting that answer?
Yeah, I got a 2.106.
Okay, so let me, I think I checked my answer. I'm pretty sure I did. So let's see. Do you see what you did wrong? Have you figured it
Yeah, I
out?
think so. I didn't
Okay.
do it the exact way that it was up there. I did put the 0.25 after the 195 because it showed up on my calculator as open parentheses 0.25 and then.
Usually your calculator errors are doing more than one step at a time.
Okay.
Notice what I do. I do this enter, plus this enter, divide by 3 enter. I just do it enter. That way I don't have to, then the parentheses don't get me messed up. If you notice, if you don't, you just have to you have to make sure you have enough parentheses. Like if I want to do this in one step, I have to make sure I have that parenthesis. And if I want this, then I have to have a parenthesis here and parenthesis here, parenthesis here, parenthesis here in order to do that. So I can, but I just have I've found it safer to divide it up, right? Okay? All right, let's go on to, this is 4.5, and 4.5, it's just a more advanced version of what we've already been doing. 4.5 are solving log equations, and we've been doing it from the beginning, right? Okay? All right, so I have a couple of examples here that I wanted to pull out. And this is where you are going to also start using your 4.4 laws of logs to rearrange things in ways that make solving equations a lot easier. We're going to start using some chapter 1 skills, etc. A little caveat for those of you who are in that pre-calculus camp, this chapter is going to be very important. For those of you who are taking this just for Algebra 2, you may struggle with a little bit of this. Just know you're probably not in a business calculus class, you wouldn't run into this. So just do the best you can. But it's really, we're doing the same thing we already did with quadratics. You'll see. We're going to start juggling exponentials and logs just the way any other function, okay? All right, so I have an example here. This isn't in your book, so you'll just, although I think this might be here. Note taking guide. So just a little bit more complicated, but if you know what to do with a function.
I had a quick question actually about the note-taking guide before we move on. I wasn't able to access it through PBWorks.
Oh, did I have the?
Have you guys been able to access the note-taking guide?
Nobody's emailed me, so. Did I not have? I might have still had a security thing on it. I could just.
It wasn't an issue about signing in or anything. It's like this page cannot be found or something like that. So.
I'll take a look.
Okay.
Just let me know if you want to. It's kind of a nice way to. It's again probably not as critical for you because I know you're more of the Algebra 2 track. You're not likely to take science-based calculus, but I felt like of all the chapters in the book, this is a nice, concise one that might be nice for studying. Some people like to do that. So what's the first thing I'm going to do here?
I have
We
two.
would, get rid of the negative 2.
Right. Notice what I really want to do is I want to be able to get this by itself, right? So I'm going to do, I'm solving this as if it's 12x minus 2, right? I'm just treating that like it's an x. So yes, the first thing I'm going to do is subtract the 2, right? Which is going to give me 20. And then what else?
Would you add the 2 because it's already negative?
Oh, duh, yeah, right. 24, sorry. So I'm gonna get 24
And then divide by 12?
and then divide by 12, right? So now I get this. Natural log is equal to 2. Don't need to take the log of both sides now, right? I just have a log on one side. So I'd say since natural log is base e squared is equal to x plus 5. E squared minus 5 will give me x. Simple as that, right? Really not that different. The only extra bell or whistle here is I have a little bit more going on around my function, right?
Yes.
Okay. And then if you check it out, right, you're gonna end up with, E ends up being about 2.389. If you plug that in and add 5 to it, you get the natural log of about 7.389 should equal 2, right? And if you take the natural log of that number, you should get pretty close to 2. I've rounded it, so it wouldn't be exact, right?
So quick question, I may be missing a link here,
Yeah.
but I got the 2.38 number by squaring e and then subtracting 5.
Right, so that gets x.
Okay, yes.
Then plugging it back
Putting
in,
it back in there.
I have to add
Okay.
5 to it, so I made it 7. Yeah,
Okay.
exactly.
Thank you.
So, there you go. And since I'd already simplified, I just plugged it into that part. I was confident I didn't make a mistake. If you're really not sure, if you have a lot going on and you're really not sure, you should just always go back to the original. But I mean, come on, I think we did this right. You know, I could get that part. Okay? All right. I have another example. Oh, those are, I'm gonna come back to those in a minute. We're doing also a number of applications here. Okay, take a look at your textbook, page 332. Do you notice at the top how they show you take the log of both sides? That's what we're not doing. If you have a simple exponent, if you want to, fine, it's just added verbiage, right? It makes it far more complicated. Okay, so if it's just a simple exponential, re-express it as a log and solve. Example 2 is just like one that we did. The only difference with example 2 is you've got to divide by 8 to isolate it. So we've already worked examples like this one, right? Okay. Again, take a look at example 3. Look at the solution. I mean, goodness, that's a natural log, right? But they took the natural log of both sides. Look how much more complicated that is. Take a look at number 3.
Oh, yeah.
But it just should be e to the 4th is equal to 3 minus 2x, right? Okay, so this is why I spend a lot of time having you convert back and forth between exponentials. It just makes solving equations so much easier. All right, so the first one that's going to have something new is take a look at example 4. It's actually kind of cool. Okay, let's see if I have these in here. Okay, so take a look at example 4. What do you notice?
It's a polynomial.
Yeah, it's in a polynomial form. Okay, and so I don't have to bring my. What particular polynomial form is that?
Trinomial?
It's a trinomial.
Quadratic?
It's a quadratic, right? So if you think about it, if I have a to the x squared, right, plus b to the x plus c. Anytime, notice I could also write this as like that, right? If anytime I have this 2, 1, 0, right, going on, and notice that's kind of what we have here. We have e to the 2x minus e to the x minus 6. Notice, anytime this is double that, I have a quadratic, okay? All right. Another way to look, does that make sense to you? Looks weird, but it is a quadratic.
Mm-hmm.
Okay,
Oh, yeah.
all right, okay. It's interesting. What I could say is that, I could say that e to the x, sorry, if I wanted to not see the e's, right, I could say is equal to an x, right? And notice that I could solve this as x squared minus x minus 6. If you want to see x's instead of your e to the x's, right? And then substitute back in. This is so simple, right? What do I have? 3 times 2, right? Well, now substitute back, right? E to the x, e to the x, right? Okay, and just double check it. What is e to the x times e to the x? Based on exponent rules, that would be e to the 2x, because we add the exponents. You're just not used to having exponents that have variables, right? Because we usually combine them into one. That's the weirdest part of this, is getting used to seeing this. Okay, all right?
Yes.
Kind of cool, right? Yeah, okay. Okay, so to solve it, we're not done yet. Solving any quadratic means set it equal to 0, right? Okay, so what I have is this either e to the x minus 3 to 0, or e to the x is equal to 3, or e to the x is equal to negative 2. Does everybody see that? Does anybody see a problem with one of those?
The negative 2?
Okay, if I raise base e to any power, can I get a negative number out of it?
No.
No, so that one gets tossed. Anybody not see why? E is 2.72 something, right?
Because
I cannot multiply it times itself any number of times and get a negative number out of that. And again, this is an exponential. What is that function going to look like? It's going to look like that. Never negative, right?
Yes.
Okay? So we have an extraneous solution. So there's only one solution. Take the natural log of 3 to get x. There it is. That's its exact answer, right? And then we take the natural log of 3 to get the estimated answer. Okay? Sorry about that, guys. I guess I didn't write my, yeah, this is page, I'm in the textbook on page 3.3. Textbook examples on 4.5, okay? Okay, example 5. Like I said, so you see where I kept saying, chapter 1 skills, right? Chapter 1 and chapter 2, really. Okay. Example 5. I believe, let me see if this is the wage. Yes, 3x e to the x, sorry,
yes. We actually
3x plus x squared e to the x is equal to 0.
well, I'm thinking we could pull out the x.
Pull out the x. So
I mean the 3x plus x squared. That's,
yeah, in other words, factor out the e to the
Yes.
x. Yeah, meaning separate them, right? So if you notice, I've got an e to the x and an e to the x. If I pull out e to the x, I'm left with
3.
x squared plus 3x, or the other way around, right? And I know what to do with that.
Yeah.
Okay. So let's take this one first. E to the x equals 0.
Yes. That's false.
Can I raise it to any power and get 0? I know what the graph looks like, right? I know the graph looks like that. Can I ever get 0? No. That's another extraneous solution, right? Okay, so that's taken care of. That's just gone. So now I've got a simple quadratic here. Factor this baby out, right? And I get x is either equal to 0 or negative 3, right? And then the only thing I ever do is go back and see, is there anything up in my original problem that would violate a domain and range limitation? But remember, our exponents can be negative, right?
Yes.
Negative exponents will just give us those fractional parts. This is one reason why the graphs are actually really nice. Because you can, if you have a little picture in your mind of what this looks like, right? It kind of answers a quick question, like you don't have to remember a rule, right? I know it doesn't go below. And this is where if I have negative exponents, oh, those are fine. I can have negative x's, right? I'm just going to get fractional answers, right? Okay? All right? So both will be true. Okay? Example 6. All right. Oh, we've already done these, basically, right? Maybe not. It might be a little bit different. Not really, right? It's base e. E to the 8 is equal to x. No big deal, right? Okay? And then if you want to break it up, that's going to be a pretty darn big number. Take a look at B. So this was A, B. This is what it says on the... Sometimes I don't know if I wrote the whole... Yeah, so here. This one's more than one way to do this one, so we might talk about this one. I don't know though. Yeah, I think I'd still be doing the same thing, right? These are easier than the ones we were doing. Again, I'm thinking to myself that 2 to the third is equal to that, right?
Yes.
So, that is equal to 2 to the third, or just 8, right? So negative x is going to equal negative 33, correct?
Negative 17.
I'm subtracting. Sorry about that. And then plus plus, right?
Yeah.
Yeah, so x is equal to 17. I don't know why I'm looking sideways at things and getting dyslexic. Okay, all right, example 7. So far, 4 and 5 are the only two that, like when you start work, you'll actually run into situations where we might use factoring by grouping with these little e's. You know, there's all kinds of, so just recognize differences of squares you're going to start seeing, perfect square trinomials, all that chapter 1 stuff that we did, patterns, you're going to start seeing these with your exponentials and your logs, okay? So if you can recognize them, you can use all of those techniques, and then it's a matter of making sure you don't have a domain, restriction, something that's creating an extraneous solution, okay? So, example 7, I don't think this one's really that big of a deal. Again, we've already been doing these. They just take practice, right?
Yes.
Step 1, isolate your log by subtracting the 4, right? So I'm going to get 12 here, and then I'm going to, so this goes away, and then I'm going to divide by 3, right?
Yes.
And so I'm going to get the log of 2x is equal to 4. Okay. How do I re-express this in exponential form?
Get 10 to the 4th
Yeah.
equals 2x.
10 with 4 zeros, right, is equal to 2x. So just divide that by 2. X is half of 10,000, right? X is equal to 5,000. Simple enough. Okay?
Yes.
Does this feel fast, Michael? Are you?
Oh no, I mean I'm following. I was just
Mhm.
shifting from other problems I was trying to work to help understand things over there.
Just making absolutely sure you're following along there. Okay. I may go back. It is Friday, right? I think I might have saved a few of the other examples for it. So from example 8 on, I'm going to actually go ahead and do example 8 because you guys just worked on your laws of logs. You're not going to, I don't think I have any homework problems yet at this level. I think I saved those for next week. But take a look at something like this. This says, solve the equation, the log of x plus 2 plus the log of x minus 1 is equal to 1. Well,
This is the addition rule, so you
Yeah.
could just multiply.
Yeah, they're both the same base, right?
Mhm.
So I could re-express this as the log of x plus 2 times x minus 1
Oh, okay.
is equal to 1, right? Which gives me a quadratic. The log of x squared plus 2x minus, so plus x minus 2 equals 1. How would I get this to a nice solvable form? I don't want to factor and go backwards, right?
Complete this
10 to the 1 is equal to this, right?
one. Mhm.
X squared plus x minus 2 is equal to 10 to the 1, or 10.
Oh, okay. And then
Mhm.
And it's a quadratic,
subtract.
Uh-huh. right? So, x squared plus x minus 12. Does this factor? 3 times 4, right? What is it? Plus 4 minus 3.
X
So,
equals-
x is either equal to negative 4 or positive 3.
Mhm.
Last step would be
to plug it back in.
plug it back in and see if I have a domain or range limitation. So,
No, there's no domain limitation.
No, because you're not going into the negatives.
can I get?
Wait a minute. Yes, you are. Never mind. So, for the negative 4, if you plug it into both of
Can I
them,
get a negative number as my answer?
so it has to be 3. Okay.
So the negative 4, try it, plug it in, see what happens. You're gonna get an error. Try to do the log of negative 2. Log negative 2, what do you get?
Bogus.
Yeah.
Not real answer.
Yeah, it's not, so this one, if you're not sure, plug it in, right? So again, we have graphs, this is gonna be a base 10 version of this, right? So the 3 is perfectly fine, right? Either way,
Okay.
I don't get a negative. If this was x minus 6, even the 3 would not work here.
Mhm.
So I'd have a problem with that, but you usually have one. There is such a thing as no solution. And I've had situations where neither one of them will work. That can happen. Just try them both.
So it's like he did all this work with
Yep.
this big equation and there's no answer.
Yep, it happens.
Well, this one did come out to be nice.
Yeah, it did.
Yeah.
Nice little
Okay,
bow.
all right. Okay, so it's not that terrible, right? I mean, just be careful. If you did your 4.4 work and understood your laws of logs, notice I can combine them and then I've got my x's all in one place, create a quadratic, use my quadratic skills, right, to
Yes.
come up with an answer. Check for extraneous solutions after that, okay? All right? Guys, at least the people who are here seem to be handling this okay. Yeah, actually, we're going to cover compound interest because that's one you're already familiar with. The transparency of the lake is a good physics problem, but it's a little bit new. I'm going to go on to the compound interest section here on page 337, okay? And notice this is really literally doing the reverse of what we did in 4.1, right? When we were doing compound interest problems. This is when the variable, the way we were doing compound interest, we had our principal, right? And we were looking for that future amount, okay? And given certain things. I think we may have already, so if you had something along the lines of, the future amount, right, is going to equal the principal times 1 plus the rate over n raised to nt, right? We worked with that a lot, okay? So the point is what if I know my original principle? We already have done one of these, right?
Yes.
Where I have an amount I want to target, say, for saving up for something, then what time period, right, would I have to, or how, what kind of compounding. So if we take a look at example 11, okay, right? If P is equal to 5,000, the rate is equal to 5%, right? Now, what did they ask me here? First of all, what if I did semi-annual compounding, and I want to find the time required for the money to double. So if it's semi-annual, right, then n is going to equal, what's semi-annual mean?
Twice a year.
Twice a year, yeah, okay. So I have everything but t, right? If I want to double it, then I want my amount to be 10,000, right? My 5,000, and I'm gonna put this in my 1 plus 0.05 over 2 raised to the 2t, right? Just plugging everything in. So this is something to notice. If you had my algebra class, we've talked about this. There's something called the rule of 72. Does anybody remember this? Sometimes also called the rule of 70, because that's really close to it as well. And this is a rule that says that if you want to approximate, get very close to the time it takes for something to double, right? You just simply take 72 and you divide by the interest rate. And 72 divided by 5 would be, well, it's divided by 10 would be 7.2, so you just double it. About 14.4%. If you're using an even simpler version, right?
Mm-hmm.
The rule of 70 would be about 14%, okay? So the reason this comes about is I hope you can notice that if I'm asking for the time to double, then whatever this is always going to be double. And you know what happens when I go to isolate this? What happens? I take this, divide by this, and I get this. In other words, the amount I start with is irrelevant. We're talking about doubling whatever I start. I could be talking about doubling $1 going to 2, right? Okay? So I have something that's pretty simple, right? Like this, okay? In the case here, okay, I've got 5%, right? I'm expecting I'm going to come up with the 14%. That's why I put that over here. We're going to see how this works. From here, what am I going to do?
We would solve inside the parentheses.
Yeah, I could simplify this, right? What is this? 1.025, right? Is that it?
Yes.
To the 2t. And now what could I do? It might help if you look at it this way. Since we're so used to looking at logs that way. So,
Well, the base is 1.025.
so the log of 1.025, right? 2 is equal to 2t. So the time is going to equal this, right? Divided by 2. What is the time that we get? Oh, I'm sorry, that's why I'm all confused. That's a percent. These are years. This is time. Sorry about that. Okay. This should be coming up with about pretty close to 14, isn't it?
Actually, I got 0.017. Wait a second.
I got 14.035.
Hold on.
So I would do log 2
Oh,
divided by
log 2.
log of this, right?
Yeah.
And then divide by 2. I think I get 14.04 about, just a little bit over 14 years. Anybody need me to run
Yeah,
that through
I
the
got it.
calculator? It's the same thing we've been doing, right? So it is about 14 years. People who are like in the financial advising industry, finance, they use this all the time because a lot of times you just want a ballpark, right? You don't want necessarily need an exact answer, and doubling is a really common, like, oh, if you want to double your money. So at least to get a nice quick, this is a lot easier to use than this, right? But this is actually, I'll show you in a moment where it comes from, okay? Let's do continuous. If I want to continuously compound interest, then what am I going to use?
Natural log?
Yeah, because I'm going to use, in particular, I'm going to use PERT, right? If you can remember PERT.
Principal E times rate.
E to the RT, right? Pert. Not times this rate
Not
to the
times,
RT.
sure.
Yeah, no, just making sure. And notice that if I'm gonna double my money, right, that means A over P is gonna equal E to the RT, right?
Mhm.
Well, if I'm doubling my money, that's gonna equal 2,
Yes.
okay?
Mhm.
So what am I gonna do to solve this one? This is even easier, right? The natural log of 2 is gonna equal the rate times the time. I'm actually just rearranging the formula here, okay?
Well, the rate's the same, right?
Right. Let me show you something. Time is gonna equal the natural log of 2 divided by the rate. What's the natural log of 2?
0.693.
Mm-hmm. Okay. And rate is in a decimal, so 0.00 whatever that rate is. Do you see where the rule of 70 comes from? If I multiply both of these by a 10, I get about 70 divided by the rate. When you do this, you do the rate in a whole number, okay? So it's kind of cool. This is where you can just see where this comes from. So in our particular case, if the rate is 0.5, that would be awesome, wouldn't it be? Okay. Then log of this, the almost 0.7 divided by 0 should be just a little bit less than the 14. Okay? Does that make sense? Either way we do, so if we do continuous, we get 13 point, I think it's 86 years. Versus the 14.4 if we use the original compounding semi-annually. So we don't pick up a lot, but we can pick up a little bit, right? A few months. Doubles a few months earlier, okay?
Yes.
So the only example I didn't work was the transparency of a lake. I think I'm gonna save that one for next time. That one's a little bit more complicated, and we've still got time next week. Okay, let's do a few more example problems, okay? I'm saving very little in this chapter for Tuesday because, like I said, I have a logarithm game that I want to, it's a really nice review game that I want to do on Tuesday. So it would be nice if you send me your homework questions in advance so that I could know how to plan that beginning time and make sure I'm leaving enough room for that. Okay, we're just gonna work a few problems here, including one that this is one more type that we have not worked yet. This is number 21. This is page 338, number 21. Okay. 5 to the x is equal to 4 to the x plus 1. Can't use my technique of expressing, so this is one that you just have no choice. You're gonna have to work with logs on both sides. That's okay. Okay? All right. So you have a couple of options. The way that, trying to see which way. The book would say, hey, take the log of 5 to the x is equal to the log of 4 to the x plus 1, and then using my power rules, right, I'm going to bring that in front. I'm going to get x times the log of 5, right, is equal to x plus 1 times the log of 4. And I have to do some distribution here, okay? X log 4 plus log 4 when I distribute this, right? These are the most tedious ones. Where do I go from here? I can't divide by x. Not What would be my next step here? This is a chapter 1 skill.
Can you,
Can I?
for the logs on the right side, can you multiply the 4?
No, this is log 10 to the 4.
Log 10 to the 4, okay.
10 to the 1 is equal to 4.
Oh, I'm saying you can't use the product law for this.
No, I don't want to.
No, okay.
I don't. So I'm trying to get x by itself. So
Okay.
here's what I do.
Oh.
Why do I do that?
It's distribution.
Well, now I can factor the x out, right? Okay, so I could say, hey, x is x times,
Log to the 5th minus log to the 4th.
these are, I don't give you tons of these, right? But, because they're tedious, and then to get rid of x, I divide by,
Log to the 5th. Nice log to the 4th.
that's dividing by, and get rid of that. So now I finally have x isolated, right? Now let's just pull out a calculator, right?
Yes.
So there is one other way to work this. I'm gonna work it a second way and see which way you like it best, okay? Okay, but see what you guys get for this here. About 6.2, I think. There's a lot of, I might do log 4 enter,
Yeah.
or I might do, what I might do is do this one here. I don't know, however you, you should get about 6.2. Make sure you can get that.
It's like so tedious.
It is so tedious, I agree. So like what I might do is say, I might do it this way. I might do log, let's turn it on. I might do log 5, right, with a parenthesis.
Oh, yeah, I see.
Minus log 4. I might do my denominator first, and then I might say, hey, log 4,
Just capture it.
right, divided by that. That might be one way. Oops, I don't know where I did that. Capture that. 6.2. Yeah, more than one way to do that. Okay, so that's method 1, okay? There's another way to do this. Okay, I'm going to show you method 2. You can choose which way you want to do it. The other way involves just picking a base and expressing them, choosing one of the two sides, expressing the whole thing as one log. Because this is the most complicated exponent, I might go here. But here's what I'm going to do. I'm going to say log base 4 to the 5x is equal to x plus 1. Does everybody see how I can do that?
Yes.
This is going to be simpler. Okay? The other way is the way the book shows you, but I kind of like this because I've only got a log on one side. So what I did is I said 4 to this is equal to this. I also could have said it this way. I could have said log 5, right? Base 5
It's 4 to the x.
to the 4 to the x plus 1 is equal to x. I could have done that as well, right? Do you see how either one's going to be correct?
Yes.
Michael's not sure yet. So there's a reason I did this one first. To me, it's easier to say, hey, 4 to the x plus 1 is equal to this.
Okay.
Or I could have said 5 to the x is equal to that. And as complicated as that look, the power rule undoes that right away, right? But I like this one better. Okay, you have a choice, okay? And then of course my x is gonna come in front. I'm gonna do that immediately, right? Okay? And what I can then do is subtract my x from both sides, right?
Yes.
Factor out my x.
Mm-hmm.
Divide, right? By the log 4, 5 minus 1, right? And x is equal to that, okay? So, I'm kind of a fan of this. Again, I've never seen a book show you how to do this, but to me, I don't know why you wouldn't. This to me is simpler. Sometimes, occasionally I've found it a little bit simpler to do it the other way. The other way will definitely be simpler if one of the two sides is either a base 10 log or a natural log. Then taking the log of both sides is going to be easier, but, okay?
Yeah.
And if you do this over this, you should get exactly the same answer. So I would probably do my, I just realized, yeah, sorry guys, chat. You can speak up. Yep, there you go. I realized I didn't release the calculator, but I'm going to go ahead and do this one. So I'm going to do my log part first. Log of 5, right? Divided by the log of 4, right? And then I'm going to subtract 1. And then I'm going to do 1 divided by that. I'm just being every little step. And I get 6.21. Same exact answer.
Yeah.
Okay? Actually, so that would have been, do you see there were 3 completely different ways to solve that, right? I could have taken the log of both sides. I could have taken the natural log of both sides, right? I could have done that. That's an even different way of doing it. But I'm a fan of choose, if I have, whichever one has the most complicated exponent, it'll put it over on the other side, right? So it's kind of a nice way to do these, okay? All right. Number 22. So I'm just going to work a few more examples here at class. This is a good example of what I just talked about. Can't express them in the same base. What happens if I do take the log of both sides? That disappears. Everybody see that? So, like I said, if you notice, like if this was a natural log or a base 10, then you actually are, it's going to be the same as if you had expressed 1, okay? So I'm going to get 1 minus x is equal to x times log of 6, bringing that over, right? Okay? Next step, add my x to both sides. What am I doing? Making sure all my x's are on one side so I can factor them out, right? And then divide. Same thing we just did a minute ago, right? X is that over that. Okay. If you want to plug that into your calculator, you would get about 0.5624. Okay, I am going to do one more of these here, because these are the ones that people have. What time do I have? 10:30 already. Of course it is. Yeah, I may skip that one. Okay. Okay, just a hint. I'm not going to work all of 23, but I'm going to get the setup, okay? We're going to talk about what might be the way. This is one of those, I've got 3 to 4 different ways to do this, right? I could take the log of both sides, I could take the natural log of both sides, or, I didn't write the whole thing down there, right? There we go. or I could express it as a base 2 or a base 3 log, okay? They both have a fair amount going on. This is maybe a little bit more, so I would say, hey, I think I'm gonna do it this way. Log base 2, right? This is my answer, is equal to the exponent. That's good. Just, again, go back to, right? Base, exponent, answer, right? All I've done, and so now I only have, this is my preferred way. I prefer to work with one log rather than two, okay? And then notice in a way I really do have two if I'm gonna use change, they really change a base, right? And that's, I think, is why the books, you do it because some people would just prefer to keep everything in log 10. And I think when you were doing slide ruling, you did everything in base 10 because you did with old slide rules and stuff like that. But now we're gonna bring this over, right? Okay. So this one's gonna be a little bit more complicated. I'm gonna leave it here and leave you to finish this one, okay? All right. And again, the strategy, the way I look at it, by the way, be careful, right? It's gonna be this times that, okay? So I'm gonna have an x times this, and I'm gonna have a 3x to bring over here, factor out my x and solve, okay? So that one's partially done. I think the solution has it the book's way, and I've got another place where I worked it out another way. Let's take a look at number 29. E to the 2x minus 3 e to the x, right? Is that what this one is? 29, right? Plus 2. If we're going to solve, we already know this is a quadratic, we're going to be doing that, okay? I don't know if that's in the book, but I know I'm going to have to do that, right? Whenever this exponent is half of that, or that one's double that, right? What can I do? I could try factoring. I'd say, hey, yeah, -1 times -2, right? That would work. So I might just go ahead and do this. If I do e to the x times e to the x, that's what's going to give me e to the 2x, right? And then I have my 1 times my 2, negative, negative, right? Okay? So my solutions is e to the x is equal to 1, or e to the x is equal to 2. One of these I know right off the bat.
1.
Yeah. E to 0. So I already know that this is a 0. Okay. X can be 0, right? The answer can't be 0, but x can be 0. Okay? Because it crosses the y-axis, right? So this one here, natural log, right? 2 is going to equal x. I already know that's going to be 0.69 something because we just did that one a few minutes ago, right? Okay. All right, so that's, we're doing one of those. You'll have right across something like that. How about number, I think you're going to be fine with something like that. 59, making sure I'm here. Okay, this is a graphing calculator one. Let's just say you're solving, right? And if you notice that if I put everything on one side, right, I get that. And I can put this into my y equals, okay? I had it, like I said, there was two options, but if you notice your calculator might hiccup if you try. I could put this in, equals this, and look at where the two intersections are, those would be solutions. But if I do it this way, my x-intercepts will be my solutions, right? Because I'd be solving this equal to 0. So let's go ahead and put this one in the calculator. Clear these guys out. And what do I have? I have the natural log of x
Plus x.
plus an x minus a 3, right? And, whoops, be careful. Gonna see what happened there. I can insert parenthesis. There we go. So double check it before you go on your merry way. I'm gonna just maybe see if it fits in a 10 by 10 window. And it does, okay? How would I find that 0 on my calculator?
Trace.
Yeah, I can
Toggle over
trace
to
it.
or-
I'm gonna get fairly close. If I wanna get a really nice estimate, like within 4 or 5 decimal places, what would be the best way to do that?
Second function.
Calc the 0. Calculate the 0, right? Okay. There it tells me left bound. Oh, yeah, I'm to the left of it. And then I'm gonna now want to go use my little key here to go to the right of it. Skip the guess, and there it is, 2.20794. So if you were asked for 5 decimal estimate, that's how you would do it, rather than just tracing over there. Okay. All right. All right. There are for those of you doing pre-calc, there are going to be several that are in this chapter that there's going to be a number of problems that are just going to be for you. Just to give you a little bit of a hint of what's to come. I actually have one. This is number 67 if you want to see my solution. I had to do a sign chart for it. So I'll give you a little hint on that one, but there are some that are a little bit challenging in there. Not tons of them, but some of them, okay? Number 71 I have on here. Number 71 says, find the inverse. So, really what are they saying? Well, this is an exponential. Find the
So
log.
just find the log.
Right, exactly. Find the log, the equivalent log expression, right? Okay? So in other words, if we're thinking in terms of, what we really want to do is, I kind of like Rebecca's idea, just go ahead and swap your x's and y's to begin with, right? Okay? And so what would I do here? Well, this is a log, right?
Yes.
Base 2, answer is x,
Yes.
is equal to 2y. So the whole expression would be,
Divide by 2.
yeah, divided by 2. There you go. Right, simple enough. There is your inverse. Okay? You can check it, believe it or not, if I put this in for that, right? The 2 would cancel the 2, right? And then I would have x times log base 2x. I'm trying to remember. Yeah, if I re-expressed it, I would end up isolating. The 2 would cancel, and all I would be left with was x. So, okay. Examples 11 and 12. I did not do. I might. No, I did. I didn't do. Yep. I did those. So, SB page 152. Last 10 minutes. So what I'd like to do with the last 10 minutes, there are 6 problems on there, okay? And this is just basically in-class group work. I have a very small group today, but like I said, kind of like what we were doing before, this is you practicing, okay? I want you guys to get to the point where you're comfortable doing these when you get into your homework, right? Okay. The more you do them, the easier and faster they get, right? The less mistakes that you make. So this is SB page 152. Practice problems 1 through 6. And these are for you to, I'm gonna put some hints up as if you need them. But this is for you to work on your own, okay? Oh, you actually, what did you
Well,
get?
I didn't.
What did you get? So we want an x. We want to solve for
Yes.
x.
I haven't finished it.
So this is one where they're the same base.
Mm-hmm.
Do you see why this is really helpful? What is x?
Five.
Mm-hmm. Do you see that, Michael? If you did all your juggling, like let's just say you moved this over and then you got a number there and then you solved for it, you'd end up probably getting something very, very, very close to 5, but not exactly 5, right?
I moved the log 2 over.
Right.
Yeah.
And you with your if you let's watch what happens if you do that, right? You'd say the log of x is equal to log of 2 minus log of 10, right? What's kind of funny about this is what happens if we're doing subtraction is the same as
Oh, okay. You're gonna get a.
this is kind of cool. I get the log of what? 10 over 2.
Mm-hmm.
Is it the way around?
2 over 10.
Yep, I was gonna say, it should be 10 over 2. Do you see? 10 minus 2? So 10 over 2 is the log of 5. X is equal to 5. That's
Okay.
you could have done it that way, right? Kind of cool. Okay. Definitely wouldn't want to do that with just a calculator, right? Okay. So go on to number 2. Again, another one, not so hard if you remember your laws of logs from 4.4. Hopefully your first step you got here was,
Is X 1?
yeah. So once you have this, 8 to the 1/3, right? Well, 8 to the 1/3 is just 2.
Mm-hmm.
2 times 1 is 2.
1.
1. X is equal to 1. Kind of cool. To me, it is. I mean, what's interesting about these is they look so complicated, right? But if you just apply a few of these rules, right, you're gonna be in good shape. Okay. Number 3. What's the first thing you ought to do with number 3?
Move the 2.
Yes. This. Move this up to here. What does that allow me to do?
To divide it.
Now I can combine these two, right?
Mm-hmm.
So this becomes the natural log of
X divided by
X
natural log.
over 3, right?
Mm-hmm.
So now express it. E to the 4th is equal to x over 3. X is equal to,
Wait, wouldn't it be x over 9? Because when you moved the 2, you made it 3 squared, which is 9.
oh yeah, I didn't, thank you. That's me not looking at my solution either, right? There we go. I said to do it, then I move it, right? Yeah, don't do that. Okay, so this becomes natural log of 9, x over 9 plus 4. E to the 4th is equal to x over 9, so x is equal to 9e to the 4th, right? Pretty simple. Could I check it to be absolutely certain?
Yes.
Yeah, I could. I could get a value for this on my calculator and plug it right back in here, right? Okay. Do you want to work through one of those? You guys have that?
I got
You
it.
got it? Yeah, we did a lot of calculator practice today. I was hoping to get through at least 4, if not all of these. Okay, how about this one? Same thing, right? Get this up here. So now I've got the natural log of x plus 1 plus the natural log of 25 is equal to 0, right? The natural log of x plus 1 times 25, I might as well. Okay. this times this. 25x plus 25, right, is equal to 0.
Or that's a minus.
Is it a minus?
Is it?
Minus
This is a minus.
Mhm.
So this means this is a minus. Thank you. It's on my key, right? I'm just not writing things on the board, right? Okay. So e to the 0 is going to equal this. What does that tell you? E to the 0 is equal to this.
Mhm.
What's that?
1. Well, e to the 0 is 1. So,
So
It's just
25x is equal to, no? This is equal to 1, this whole thing, so if I add is equal to 26,
yes.
x is equal to
26.
26
over
25ths, right?
Yes.
So as a pony running for the barn door, we look for something, it's also our wishful thinking, right? Something having an answer that simple.
Mhm.
Right. The last two are also integer answers. You guys have time to work. They're all the same base, right? So the first thing I'm gonna do, right, is do that. So I'm gonna get log of x to the half minus log of 2 cubed, that'll be 8, right? Okay.
Yes.
Plus the log of 20. What can I do now? Put them all in one log, right? The log of x to the 1/2, or the square root of x, either way you want to put it, right? Minus 8, right? Which means divide by 8 times 20, okay? Is equal to 1.
Okay.
So,
I could take out a 4 out of this one, if this is times 20, right?
mhm.
Let's say, well, divide by 4,
Mhm.
right? That leave me 5 there, okay? Maybe simplify it a little bit. Okay.
Hmm.
So, base 10, 10 to the 1, right, is equal to 5 square root of x over 2, if I want to do it that way, right? So multiply by 2/5 each side to get rid of that fraction. That goes in 2 times 2. The square root of x is equal to 4. Just a lot of arithmetic, right?
Mhm.
X would equal
16.
16, not 2. I sometimes go backwards on those, right?
Mhm.
Okay. So far, so 2 log 3x minus 1/2 log 316 equals 2. Bring those over. They're both log base 3, so I've got 3x squared minus log 3. When I do x to
That
the
would just
1/2, that's just going to be
4.
4, right? So when I take this over here, I just get the square root of 16, which is 4. So that cleaned up rather nicely. Log base 3. What do I get here? This over that, right? X squared over 4 is equal to 2. 3 squared, which is 9, is equal to x squared over 4. Am I going fast? Too fast?
Answer 6.
Huh? Yeah. Times 4, 36. X is equal to,
6, 6, 6.
technically it could be plus or minus 6, but do you see why you throw out the minus?
Mm.
Do you guys see that?
Yes.
If I'm solving as a quadratic, but the minus. I can't get a -6 in that place. So just beware, right? If I had a different expression that I could accept a negative, but. So 6 really good practice examples. That's the kind of stuff you're gonna be juggling around for homework on Monday or whenever you do it. Okay, all right. Any last minute questions? Excited, Hannah?
Thank you. Yeah.
I think they're kind of fun. I mean, you're just basically doing algebra. Now, this is why the functions chapter is so important. I mean, you're just doing the same thing. You're going to do the same thing with trig functions. If you're comfortable with learning to juggle these like they're numbers, then, you know, isolate them and then do the function. And then when you do calculus, that's what the chain rule is going to be about, is I've got different functions within functions. All right, I'm going to put the board, oh, okay. Remember,